Welcome to This Explainer. Today, we're going to completely transform how you view the Arduino ecosystem. Look, if you think this is just some toy for weekend hobbyists, well, think again. We're mapping out the entire journey here, all the way from a beginner making their very first LED blink, right up to industrial-grade, fully automated factory systems. It's going to be a wild ride.
So here's our roadmap for today. We'll hit 1. Bridging code and reality. 2. The language myth. 3. The hardware family. 4. The software ecosystem. 5. Arduino versus alternatives. And finally, 6. The reality check. Let's get right into it.
Section 1. Bridging, Code, and Reality. So, what exactly is Arduino?
At its core, an Arduino is built around a microcontroller. Think of it as a tiny computer on a single chip, tailored specifically for real-time control, but without a heavy, full operating system. Unlike the laptop or the phone you're using right now, which are built for, say, running big screens and heavy apps, Arduino has one pure purpose: bridging the gap between digital code and physical reality. It's out there, literally listening to sensors, flipping switches, and controlling motors in real time.
Moving on to Section 2, the Arduino language myth. Let's look at the C and C++ under the hood. Okay, you'll often hear folks say, "Oh, I'm programming in Arduino." But guess what? There is absolutely no distinct Arduino language. Under the hood, it's just standard C and C++. What the brilliant creators of Arduino actually did was wrap that super complex code in a simplified API, or application programming interface. This wrapper is literally a game changer because it makes hardware control incredibly accessible. It totally removes the steep learning curve of raw C++ microprogramming.
Because of this simplified API wrapper, every single program you write, which in the Arduino world is called a sketch, relies on an exact two-step anatomy. Step 1 is the setup function. This runs exactly once, right at the moment the board powers on. It's where you essentially tell the board, hey, these pins are inputs and these ones are outputs. Then, step 2 is the loop function. Once setup is done, this loop runs repeatedly, forever, executing your main logic. It checks a sensor, turns on a light, checks the sensor again, turns the light off. Over and over, infinitely. It's beautifully simple, yet incredibly effective.
All right, Section 3, the hardware family. We're going from Uno all the way to industrial.
Now, you might think Arduino is just that classic blue beginner Uno board you've seen in a million tutorials. But wow, the ecosystem has scaled dramatically. Sure, we still have the Uno R4, which is absolutely the undisputed king of prototyping and learning. But then, check out the brand new Uno Q. This thing is a massive shift. It's a hybrid board co-developed with Qualcomm that actually combines a Linux microprocessor with a real-time microcontroller, specifically aimed at driving edge AI and computer vision. Crazy, right? Then you've got the Nano family, shrinking everything down into these tiny footprints perfect for wearables or tight space IoT projects. And finally, the Portenta and Opta lines. These aren't toys. They are professional industrial-grade boards and micro PLCs built to power serious factory automation. Arduino is, for sure, no longer just for hobbyists.
Which brings us to Section 4, the software ecosystem. Tools for every level.
Just like the physical boards, the software scales up dynamically to meet you wherever you are. It all starts with the Arduino IDE, that classic, super familiar desktop app where beginners write and upload their code. But as you graduate to professional engineering, you move over to the Arduino CLI. That's a powerful command line tool designed for building automated integration pipelines. Now, if your project needs to live on the internet, there's the Arduino Cloud, an online platform for rapidly deploying IoT dashboards and monitoring remote devices. And for those advanced hardware boards we just talked about, well, we have specialized tools. The App Lab for visual edge AI programming on the Uno Q, and the PLC IDE built specifically for industrial automation workflows on the Opta.
Next up, Section 5, Arduino versus alternatives. Let's see how it actually stacks up. The most common debate you'll hear is Arduino versus Raspberry Pi, right? But honestly, they're built for completely different jobs. Arduino is the undisputed master of real-time, predictable hardware control and low-power sensor reading. Like when you press a button, it reacts instantly, every single time. The Raspberry Pi, on the other hand, is a full mini-computer running Linux. It's designed for running web servers, handling heavy computing tasks, and managing complex networks. Simply put, you wouldn't use a Pi just to blink an LED, and you definitely wouldn't use an Arduino to host a heavy website. So where exactly does Arduino fit alongside other microcontrollers, like the mega-popular ESP32 or the professional STM32 chips? The relationship here is super fascinating. The ESP32 is famous for its low-cost Wi-Fi, but it's not actually a competitor. You can actually program it entirely using Arduino software tools. And for the complex mass-production STM32 chips, well, Arduino serves as the core rapid proof of concept. You test out your idea quickly on an Arduino, and then when it's time to manufacture 1,000,000 units, you make the leap to the STM32.
And now we reach Section 6, the reality check, going beyond the basics.
Let's get real for a second. There is a profound truth in the engineering world. Arduino is the absolute best tool for learning electronics. However, it can encourage bad habits. Because the API is so simplified, getting a prototype to work on your desk is incredibly easy. But, it kind of lulls you into a false sense of security. While it's an unmatched learning tool, you really must be extremely careful not to get trapped into beginner's mindset when you're trying to build something for the real world.
So what do those bad habits actually look like? Well, the biggest offender, hands down, is relying on the blocking delay function. In the typical beginner tutorial, if you want a light to blink every second, you turn it on, use a 1-second delay, turn it off, and use another delay. Super easy, right? But here's the catch. A blocking delay literally stops the processor from doing anything else. If you're building a commercial product and your whole system is just paused, waiting for a light to blink, it might completely miss a critical sensor reading or fail to trigger an emergency stop. Relying on delays, or, throwing hundreds of lines of messy code into one massive loop file, will absolutely sink a commercial product.
To actually graduate past those beginner tutorials, developers have to apply strict engineering discipline. I'm talking about implementing strict power management so your device doesn't just drain its battery in an hour. You need to build in over-the-air or OTA updates, allowing you to fix bugs remotely without having to physically plug the device into a laptop. You've got to ensure highly efficient memory usage because, remember, microcontrollers have tiny amounts of RAM. And finally, you need bulletproof failure recovery so that if a sensor disconnects, the whole system doesn't just crash and burn.
I want to end this explainer by leaving you with a provocative question, something to really challenge your engineering discipline moving forward. Your prototype works perfectly on your desk, but will it survive the real world? Arduino gives you the incredible power to bridge the gap between code and physical reality. It scales all the way from the simplest blinking LED right to the factory floor. But taking that final, crucial step from a desk prototype to a robust, real-world product, well, that part is entirely up to you. Thanks for joining me on this explainer today. Keep building, keep learning, and I'll catch you next time.